The starting point is to write Schrödinger equation in steady state, where P is the momentum operator, V the electrostatic potential, E the energy, and psi the corresponding wave function of the electron that we're trying to find. We recall that the potential is periodic and can therefore be expanded upon a set of plane waves, which reflect for the periodicity of the lattice. We will assume that we know the potential and therefore the values of the coefficients V of k. For a 1D potential with period A, the lattice vectors would be R equals n times A, and the wave vectors k would simply be k equals m times 2 pi over A. For a 2D potential, the wave vectors k form a lattice known as the reciprocal lattice, which, just like the real lattice, has primitive vectors b1 and b2. The important properties is that b1 is orthogonal to a2 and b2 is orthogonal to a1. Besides, the 1D relationship holds for a1b1 and a2b2. With these properties, it is straightforward to check that v of r plus capital R equals v of r. The plane wave method consists in looking for the wave function psi in the form of a linear expansion of plane waves. Each plane wave is described by a wave vector q, which has a direction, and a wavelength lambda equals 2 pi over q. C of q are the unknown amplitudes of the waves, which we will be solving for. It is important to notice that these waves may not have the same periodicity of the crystal. This is therefore also true for psi. We can, however, reasonably anticipate the electron density psi squared to have the periodicity of the lattice, although we are not enforcing it. So let's inject our expressions for V and psi into Schrödinger's equation. Let's express wave numbers in units of k0 by using lattice constant A, and express energies in lattice Rydberg units to get rid of the constants in these equations. For the sake of completeness, the following part of this video is dedicated to the rigorous derivation of the method, and will therefore be a bit mathy. The important takeaway will be summarized in the next section, so feel free to use the timecodes to skip this. Okay, so we can see an opportunity here. If we choose a given value of q prime, multiply both sides by the conjugate plane wave, and integrate over unit cell, this would allow us to isolate an equation for that particular value of q prime. But we first need a sum involving k plus q to run over q. Therefore, we just write that q becomes k plus q, so c of q becomes c of q minus big K, and rearrange the sum. We now use our trick to obtain a system of algebraic equations for all possible plane waves q. We can notice that any plane wave q couples with plane waves q minus big K, so only with those involving a reciprocal lattice vector big K. Besides, for any vector q, which can be taken anywhere in reciprocal space, there must be a particular reciprocal vector k such that q plus big K lies within the reciprocal unit cell about the origin. We denote any such vector little k. Since this particular reciprocal vector big K is different than the one in the sum, we'll replace by k prime in the sum and inject our expressions for q, which, after rearranging the sum, gives us our final expression of the system. Writing our system with matrices and vectors, let's see what the HQ matrix looks like. Let's choose for our set of plane waves two arbitrary vectors, little k1 and little k2, and four others that we build using big K1 and big K2. For the first equation, we use q equals little k1, which couples with little k1 minus big K1 through v of big K1, and to little k1 minus big K2 through v of big K2. For q equal little k1 minus big K1, the coupled terms involve little k1 through v of minus big K1, and with little k1 minus big K2 through v of K2 minus big K1. And similarly for q equals little k1 minus big K2. Now for q equals little k2, Coupling involves little k2 minus big k1 and little k2 minus big k2. And similarly for the remaining waves. So this system is, as anticipated, block diagonal. This means we can break this big system into a set of independent systems, each corresponding to a wave vector k lying in a single unit cell, also called the first Brillouin zone. In the previous section, we've seen that by expanding the electrostatic potential on the reciprocal space lattice, and by using a linear expansion of plane waves for psi, Schrödinger's equation reduces to a set of eigenvalue problems where the eigenvectors are the coefficients of the expansion C of k. This can be solved by diagonalizing the Hamiltonian matrix. There is an eigenvalue problem for each wave vector little k, which may lie anywhere in the first Brillouin zone. If symmetries exist, such as in the case of a square lattice, we can restrict k into an asymmetric cell, and use the symmetries to get the solutions from the asymmetric cell to the full first Brillouin zone. The crystal is technically infinite, but we need to truncate the number of reciprocal lattice vectors, big K, to a computationally tractable set. For this example, we'll only use the following 9 vectors for big K, to which correspond the following plane waves considered for this particular vector little k. The diagonal part of the Hamiltonian matrix are the kinetic energies of the plane wave, for which each entry can be labeled with its reciprocal lattice vector. Although this can be a complicated aspect of crystal physics, we'll assume some values for the Fourier coefficients of the electrostatic potential, which would correspond to the following potential in real space. The off-diagonal part of the Hamiltonian correspond to the cross-coupling potential terms. So now that we have defined everything, let's write the code for this problem and see what solutions we get.